Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System, Lecture 35, Saturn. In this lecture, we're going to look at the second largest planet in our solar system, the planet Saturn, which of course is famous for its immense ring system. But first, let's talk about some basic facts about Saturn. It's 9.5 astronomical units from the Sun, so not quite 10 times further from the Sun than we are. Its orbital period is just a little bit less than 30 years. Its orbit is inclined by about 2.5 degrees with respect to our orbit around the Sun, that is, with respect to the ecliptic. And it's a pretty circular orbit with an eccentricity of 0.056. The diameter of the planet is 9.4 times the diameter of the Earth, which means that it's just a little bit smaller than Jupiter, which, as you'll remember, was a little over 11 times the diameter of the Earth. Its mass is 94 times the mass of our planet, and that makes Saturn the second most massive planet in the solar system. It is also the second largest in terms of diameter. Now, what's interesting about Saturn is it's almost the same size as Jupiter, but its mass is significantly less. You'll remember that Jupiter's mass was 318 times the mass of the Earth. Saturn is less than a third the mass of Jupiter, and yet is almost the same size. And we saw in the last lecture, that's because as we add more mass to these gas giant planets, all it ends up doing is squeezing the material at the centers, squeezing the gas down at the centers into a denser and denser state. The average density of Saturn is less than the density of water. It is the only planet in our solar system whose density is less than water at 0.7 grams per cubic centimeter. And then finally, its rotation period is 10.7 hours. Saturn, of course, is famous for its immense ring system. By far the most beautiful and spectacular ring system in the solar system. So here's another close-up image of the ring system here. So some of the interesting things we can see in the ring system is we can see a gap in the rings right here called Cassini's division. This is an actual gap in the rings that is caused by one of Saturn's moons, which orbits outside the ring, but is in an orbital resonance with the particles inside the ring. So its gravity over time has pulled the particles out of that gap. We can see the shadow that the rings are casting down on the planet right there, the very, very thin shadow of the rings. And then on Saturn itself, we can see some clouds and some banding. Here's another spectacular image of Saturn taken by the Voyager 1 spacecraft a couple days after it passed the planet. It's an amazing photograph because we never get this view from Earth. You can only get this view if you are farther from the Sun than Saturn is. And of course, from Earth, we always see the lit side of Saturn. We never see Saturn in a crescent phase like this. And it's really spectacular because not only can you see the shadow that the rings are casting on the planet right there, but of course the shadow that the planet is casting back on the rings. So really a spectacular image of Saturn and its rings taken by Voyager 1 as it was headed out of the solar system. So quickly, let's talk about the discovery of the rings for a second. It was Galileo with his telescope who first noticed the rings in 1609, 1610. The thing is, Galileo didn't understand what he was seeing. He variously interpreted Saturn as being made of 3 parts, a planet with 2 other parts. He interpreted it as ears on Saturn. He wrote to the Medicis, his patrons, to say, I discovered another very strange wonder which I should like to make known to their highnesses, keeping it secret, however, until the time when my work is published. The star of Saturn is not a single star, but is a composite of 3, which almost touch each other, never change or move relative to each other, and are arranged in a row along the zodiac, the middle one being 3 times larger than the lateral ones, and they are situated in this form. And then he draws a small o, a bigger O, and a small o. Galileo's telescope was too crude to show him the true nature of the rings of Saturn, and he didn't observe Saturn long enough to see the rings change their orientation. So, and probably influenced by his observation of Jupiter, where he saw the moons of Jupiter, he probably interpreted these as bodies around Saturn. But unlike the moons of Jupiter, which he could actually see going around Jupiter, these never seemed to change. The true nature of the rings of Saturn was discovered by the Dutch astronomer Christian Huygens in 1655. Huygens made these drawings of Saturn, variously interpreting them in different ways. But in 1656, Huygens claims to have discovered the true nature of the rings of Saturn. Now, an interesting question in these days was who would get priority for a discovery. If you announced that you had discovered that Saturn was surrounded by a thin, flat ring, it might be that others would step forward to say, no, they had discovered that before you. Because, of course, this was before the era of rapid publication of works as we have in science today. Today, if I make a discovery, I will write it up and I will publish it. And if I am the first to get the discovery to publication, I will be given credit for it. But in these days where communication was slow, there was no guarantee that someone in a far distant country would get your communication before they made a similar discovery. And there were very often arguments about who discovered what. So one technique that was used to make sure that you got credit for it is that you would distribute your discovery to your friends, but you would distribute it in the form of an anagram. So even they didn't know what your discovery was. And it wasn't until sometime later when you would reveal your discovery and all of your friends had the anagram to show that that was the discovery that you had revealed. In the meantime, should someone claim that they discovered it before you, your friends could say, no, they had sent me the discovery long before in the form of an anagram. So the anagram that Huygens used to disguise the discovery of the rings of Saturn, here it is in Latin, but it is surrounded by a thin, flat ring, nowhere touching, and inclined to the ecliptic. And he's exactly right. The rings of Saturn are a thin, flat ring. Nowhere do they touch the planet Saturn, and they are inclined or tilted with respect to the ecliptic. Now, in part, what gave Huygens this idea was watching Saturn change over many years. This was something that Galileo was not able to do. And what Huygens realized is that as Saturn orbits the sun, like the Earth, it is tilted over, and also like the Earth, it maintains that orientation as it orbits the sun. So at times, from the Earth, we will see the rings edge on, and at times, we will see the rings face on. So at times, Saturn will look like it's surrounded by a magnificent ring system, and at times, those rings will almost seem to disappear. This shows it better, I think, than those drawings. These are Hubble Space Telescope photographs of Saturn taken at various times in its orbit around the sun, showing us times when the rings are wide open to us. In other words, Saturn is at its maximum tilt, or I should say, it's presenting to us. It's the tilt is away from us at its maximum, so we can see, in this case, most of this hemisphere. And then down here at the bottom, a time when we were seeing the rings almost edge on. So those are some images of Saturn taken by the Hubble Space Telescope, again, showing you the Cassini division in the rings, that gap in the rings. There's also a little thin division out here called the Encke division. The three major rings of Saturn are the A ring, the B ring, and then the C ring in here. There's also a thin, tenuous D ring inside of that. But those are the rings of Saturn. When the rings are edge on, the rings of Saturn look like a thin, flat line. In fact, they can almost disappear as seen from Earth. It's not a great time to look at Saturn through a telescope because the rings really do almost completely disappear. Usually there's a hint of them because of the shadow that they were casting back on the planet. But other than that, the rings are hard to see. And of course, when Saturn has its maximum tilt, the rings are really quite spectacular and really something to see. Well, as Saturn goes through its almost 30-year orbit around the sun, twice during that orbit, here and here, the rings will appear edge on. So that means the rings will be edge on, and then 15 years later, they will be edge on again. And so during the course of its 30-year orbit, it will be face on twice, edge on twice. So it'll go from edge on, take about 7.5 years or so to get face on, 7.5 years to get edge on again, another 7.5 years to get face on, and another 7.5 years to get edge on. So every year when you look at Saturn, it looks a little bit different than last year. And for a few years, you can watch the rings grow, and for a few years, you can watch them decrease until they disappear. Okay. So those are the visible manifestations of the rings of Saturn. In our last lecture, we also mentioned that because of its large size and its very rapid rotation, taking a little bit less than 11 hours to rotate on its axis, the planet itself is elongated. That is, Saturn is wider around the equator and narrower around the poles. And that comes again from the rapid rotation. That rapid rotation, the centrifugal force from that counteracts the force of gravity, and that allows Saturn to be wider around the middle than around the poles. Saturn has the most pronounced effect of all of the planets in the solar system, in part because it is so big and it rotates so fast. And it has more distortion than Jupiter does, because Jupiter is about the same size and rotates at about the same speed, but its gravity is significantly higher since it is 3 times more massive. The interior of Saturn is similar to the interior of Jupiter, but because Saturn is less massive, the transition from one zone to the next zone, from one region of the interior to the next region of the interior, is buried deeper inside of Saturn. So like Jupiter, it has some kind of core that consists of those early rocks and metals and icy compounds that initially formed and that then drew in the hydrogen and helium gas, that huge gaseous envelope that Saturn has today. As we saw in our last lecture, thanks to the Juno probe, we know that Jupiter has a fuzzy core. That is, it's not a well-defined core like this, but it is spread out over a much bigger area of the inside of the planet. We don't know yet what the interior of Saturn is like. That might come from a future mission, but there are none planned right now. So we don't really know what the interior core of Saturn looks like. But like Jupiter, it's probably surrounded by a metallic hydrogen region, a liquid hydrogen region, and then a gaseous hydrogen envelope. But unlike Jupiter, where these transitions occur high up, in Saturn, we have to go much deeper down inside the planet to find those transitions. We have to go deeper down because it's less massive. We have to go down deeper so that the weight of the overlying layers can provide the weight to provide the pressure and the temperature needed for this transition from gaseous hydrogen to liquid hydrogen to metallic hydrogen. And Saturn, just like Jupiter, has belts and zones, but they're much less distinct on Saturn than they are on Jupiter. So you'll remember when we were talking about Jupiter, we said the zones are these brighter regions, the belts are these darker regions right here, and they come from material at different altitudes in the atmosphere of Jupiter. So the ammonium hydrosulfide cloud are the belts, the darker belts, they are lower down, and the whitish colored zones that are higher up are actually ammonia clouds that are higher up than the ammonium hydrosulfide clouds. Saturn will do the same kinds of things. So as the material in Saturn, because of heat from the interior, wells upward, as that material wells upward, it will condense into water clouds, ammonium hydrosulfide clouds, and ammonia clouds, just like they do on Jupiter. But the difficulty with Saturn is, again, because of its lower mass, these things will happen deeper down inside the planet. Because they happen deeper down inside the planet, when we look at the planet, it is not nearly as colorful as Jupiter. And that's because we're looking at those belts and zones through a much deeper outer transparent outer atmosphere. This upper atmosphere up here is transparent, but it does scatter some light, and so it makes Saturn's features less distinct. Now, this particular picture is of a huge storm that developed on Saturn. This picture was taken in December of 1994 of a huge big storm on Saturn. Saturn does not have the equivalent of the Great Red Spot. There are certainly storms on Saturn. There are flow patterns on Saturn similar to Jupiter, but this was a temporary storm, not what appears to be the permanent Great Red Spot on Jupiter. And then finally, we get to the rings of Saturn, probably the most spectacular feature of the planet. I've already shown you this image taken by the Voyager 1 spacecraft on its way out of the solar system. Here is another image of the rings of Saturn. And what's important to realize about the rings of Saturn is that they are not solid. The ring is actually made up of thousands of individual ringlets. Now, we'll see in a little while what it would be like to be inside the rings of Saturn, but just know now that there's not one solid band of material. It's made up of thousands of little individual ringlets. And then we have the Cassini division here, and then more thousands of individual ringlets in the Encke division, and more ringlets right there, and then this faint outer ring of Saturn called the F ring. So if you could take a close-up image of the rings of Saturn, this is a close-up image taken by the Cassini spacecraft. It shows you some of the thousands of ringlets that make up the rings of Saturn. Here is another image that shows you the thousands of ringlets that make up the rings of Saturn. The spacing that you see here has to do with the interaction of the gravity of the moons acting on the particles in the rings of Saturn, producing these really spectacular geometric shapes, these geometric figures of the material bunched. So what we're seeing here is material bunched into very thin ringlets. So what would it be like if you were inside the rings of Saturn, and what are they made of? Well, the rings of Saturn are primarily made of water ice, chunks of water ice with probably some rock and dust mixed in as well, but substantially made of water ice. And those chunks of rock and dust and water ice would probably look something like this if you were inside the rings of Saturn. Now, the problem with this is there is no scale on this. How big are these things? And the answer is the typical biggest things that we see in the rings of Saturn are probably somewhat bigger than your head, probably the size of a good-sized beach ball, maybe a bit bigger than that. And occasionally there will probably be house-sized particles as well in the rings of Saturn, but the vast majority of particles are going to be smaller than your head. But we're not going all the way down to really small particles as well. The rings of Saturn are really quite complex. The bright main rings that we see are divided into three parts: the A ring, which is the outer part, the B ring, which is the inner part, the C ring, and then inside of that is the very faint and indistinct D ring, and then just outside of that is the F ring, and then there is this giant E ring that encompasses many of the moons in Saturn's system. There's Mimas, Enceladus, Tethys, Dione, and Rhea right there. So those are some of the outer moons of Saturn. Saturn has over 60 moons orbiting around it. One major moon, Titan, which is actually the second largest moon in the solar system, and Titan itself is just a tiny bit smaller than the planet Mercury. I'll show you a better picture of the moons of Saturn here, but I liked this one because it had our moon for comparison. So you can see Titan is just a little bit bigger than our moon. And here's the better image that shows you Saturn's moon Titan and many of its other moons: Iapetus, Dione, Rhea, Tethys, Enceladus, Mimas. Those are the major moons of Saturn. There are many smaller moons and then dozens and dozens of little tiny moons that orbit Saturn. And right now we'll talk about it in more detail, that Titan, the reason that there are no features shown on Titan there or in this image is that Titan is covered in a thick atmosphere. And that thick atmosphere has hydrocarbon smog in it, and that hydrocarbon smog prevents us from being able to see down to the surface. Much of what we know about Saturn came from both the Voyager 1 and Voyager 2 missions, and in particular the dedicated Cassini mission to Saturn. So the Cassini mission to Saturn was a follow-on to the Galileo mission to Jupiter. Cassini was launched in October of 1997, and it took 7 years to get to Saturn, and it arrived on July 1st, 2004. Its initial mission was supposed to last 4 years, but the mission didn't actually end until September of 2017, 13 years in orbit around Saturn. At that time, Cassini was running low on fuel, and so at the end of the mission planners set up a spectacular series of orbits, where instead of orbiting far out in the Saturn system, the orbit was changed so that Cassini would actually orbit, at least on some of its passes, would come down between Saturn and its rings, just outside of Saturn's atmosphere. But as it ran low on fuel, scientists wanted to make sure that Cassini would never collide with any of the icy moons of Saturn for fear that it might contaminate them. And so Cassini was intentionally crashed into Saturn. It burned up in Saturn's atmosphere in September of 2017. Now, as part of the Cassini mission, it carried a probe to Saturn's largest moon, Titan, and that probe was called the Huygens probe, and the Huygens probe was released in December of 2004, and it parachuted down through the atmosphere of Titan on January 14th, 2005. So here's a picture of what the Cassini spacecraft looks like before launch. So inside this heat shield right here, that is the Huygens probe that entered the atmosphere around Titan. And then here is the Cassini spacecraft itself, the huge antenna that it uses to contact Earth. Unlike Galileo, which used that folding antenna, which you'll remember from the last lecture failed, this one antenna was permanently open. It had camera booms. It had all kinds of scientific instruments on board. The Cassini mission was an outstanding success, staying in orbit around Saturn for 13 years. It returned just absolutely stunning pictures of Saturn. I love this picture showing us the seasons on Saturn. You will notice Saturn and its rings, but you will notice the tilted daylight here, and that indicates what's actually going on is that Saturn is tilted over. The sun is down over here. And so because the spacecraft is in orbit around Saturn, we're getting this view that looks like the solar system is tilted, but really what we are seeing here is Saturn being tilted over. We can see again the shadow that the planet is casting back on the rings, the Cassini gap in the rings, the Encke division in the rings. Truly a spectacular image. If you look up here very carefully, you can see the shadow that the rings are casting back on the planet. Just outside the A, B, C, and D rings is the very, very thin F ring, and Cassini returned just spectacular images of the F ring. The details that you see here in this ring are real. It looks braided here, and these braids come about because of an interaction between the F ring and one of the moons of Saturn. In fact, that moon of Saturn is the small moon Prometheus, and Prometheus can actually steal material out of the F ring, and the gravity of Prometheus sets up these beautiful braided bands in the F ring itself. Now, Saturn's moons are absolutely fascinating. There are moons like Iapetus. Iapetus has surrounding it a famous mountain that occurs right around the equator of Iapetus. It's really quite a spectacular feature on the moon. It looks almost like we took two pieces of ice cream and squished them together, and we got this big ridge where the two of them were put together. Many different ideas have been put forth for this ridge. The one that I favor is this happens to be material that Iapetus has accreted or gathered out of the E-ring of Saturn. That is, as material in that ring came crashing down to Iapetus, the ring is thin and it built up primarily around the equator of Iapetus. But there are also models where this is a tectonic feature on Iapetus. And of course, we get to Saturn's largest moon, Titan. Titan is, as I mentioned, covered in this atmosphere. The atmosphere on Titan is filled with this organic smog that gives it its very distinct orange color and does not allow us to see down to the surface. Here's another view of Titan's atmosphere, showing you the sunlight that's sort of filtering through the atmosphere over here on this side. You see the thin crescent Titan over here, and then the sunlight filtering through the atmosphere right there. Now, this is the best view of Titan that we have ever gotten from the surface of the Earth. And as you can see, we can make out hardly any features at all. Because of the smog, we can't use visible light to see down through the atmosphere. But infrared light, with its longer wavelength, and in particular, some particular wavelengths of infrared light, can make it through Titan's smoggy atmosphere. So this is an infrared image taken from Earth of Titan. Doesn't show you much detail. The spacecraft, however, have infrared cameras, and they also have filters to allow us to see down to the surface of Titan. And this is one of the images taken by the Cassini spacecraft. This is a much better image taken of the surface. Now, it's difficult to see because we're looking through the smog. You can see as we go further off to the edges here, where you're looking through more and more smog, that it gets indistinct. But one of the most fascinating features about Titan and its atmosphere is that the atmosphere of Titan is dense enough and cool enough, and the pressure is high enough that methane and ethane can exist as liquids. That is, you could have on the surface of Titan lakes of liquid methane and liquid ethane. And in fact, they will evaporate off the lakes, form clouds in Titan's atmosphere, and the ethane and the methane may even fall to the surface as raindrops. And Cassini did see some evidence for clouds and evidence for lakes on the surface of Titan. Lakes not of water, liquid water, but of liquid methane or ethane. One of the more spectacular parts of the Cassini mission was the Huygens probe. So Huygens was designed to descend through the atmosphere of Titan and land on the surface. Now, because we hadn't seen the surface very well before the Huygens probe, they did not know whether it would land on a solid surface or whether it would land in the liquid ethane and liquid propane, liquid ethane and liquid methane. And so the spacecraft was designed to survive a landing either on solid ground or to float in a liquid. It parachuted down through the atmosphere, and as it was parachuting down through the atmosphere, it took a photograph like this. So this is a photograph taken looking down. Now, the photograph isn't very clear, and that's in part because it's still looking through a lot of that haze. It's still at this point about 10 miles, about 50,000 feet or 16 kilometers above the surface. But this is what the surface of Titan looks like from somewhat higher than an airliner on the surface of the Earth. And of course, what's most amazing about this is you see these absolutely amazing channels cut on the surface of Titan. As was expected, the liquid methane and liquid ethane must fall from the sky as rain droplets and cut river channels on the surface of Titan. At the time this picture was taken, there was no liquid on this part of Titan, but liquids have clearly flowed here in the past and cut these channels. At about 8 kilometers high, this is a panorama that was pieced together. We can see this area right here with the rivers. That is this area over here. And then there is this dark smooth region down here. That's actually where this dark smooth region is the region that Huygens set down in. And you can see that dark smooth region right here. Another image showing you channels cut on Titan right there. The spacecraft successfully touched down on the surface of Titan, and it returned data for over an hour sitting on the surface of Titan. It even returned some pictures, and this is one of the amazing pictures that it returned. So I think it's just remarkable that we live in an age where we have a picture from the surface of one of the moons of Saturn that was taken by a probe that parachuted down through the atmosphere. Now, two things about this photograph that stand out. The first one is look at those rocks in the foreground. Those rocks are round. Round rocks are only created by erosion. Those are rocks that had tumbled. Liquid water, it's not liquid water. Let me correct myself. Liquids have flowed on this part of Titan. And over time, as the liquid flowed, these objects that we see in the foreground have rolled with that flow, and they have been eroded and chipped into that round shape. The second thing about them is that those objects in the foreground are probably not rocks at all. Those objects in the foreground are actually probably blocks of water ice. The surface temperature of Titan is hundreds of degrees below zero. It is frigid. At those temperatures, water ice is frozen as solid as rock. And so what we're looking at here that look like rocks are probably chunks of water ice going off into the distance. Just to give you an idea of how big they are, these show you some of the things. So these are about 15 centimeters across right there. So this one is about 15 centimeters, and that's about 6 inches in diameter. So, that's a rock about that big. So that's the sizes of some of those features on Titan. Now, another one of Saturn's amazing moons is Enceladus, or Enceladus. Enceladus is an icy moon. It is covered in water ice, and it bears a lot of resemblance to Jupiter's moon, Europa. There are parts of Enceladus that are covered in craters, and then there are parts that are covered in stripes like this that have hardly any craters on them. These are the old parts of the moon. These, of course, are the young parts of the moon. And at the south pole of the moon, there are fissures and cracks in the surface of the moon. And from those fissures and cracks, we see material jetting out into space. And that material that jets out into space is actually water vapor. Beneath the icy surface of this moon is a liquid water ocean. And where there are cracks in the surface, that liquid water ocean is squeezed to the surface at high pressure and vents itself out into space. So here's the global ocean. There is an icy crust on Enceladus. There is a global ocean underneath and a rocky core. And where there are cracks in the surface, primarily around the south pole of the moon, that is where we get the water jutting out into space. Literally liquid water. Geysers, even more stronger than geysers, jets really shooting out into space and then instantly vaporizing. And then finally, Saturn's moon Mimas, which bears a striking resemblance to the Death Star. This giant crater Herschel here is about 130 kilometers or about 80 miles across from side to side. The creation of that crater on Mimas must have almost destroyed the moon because of the size of that crater. So this has been a fairly quick tour of Saturn, its rings, and its moons. Join me in the next lecture when we will look at both Uranus and Neptune, and we will look at their moons as well. So please join me in the next lecture for our look at Uranus and Neptune.